Hi, my name is Brian Caffo, and welcome to the Introduction to Regression lecture as part of the Regression Coursera class. This is part of our data science specialization, and this class is co-taught by my co-instructors Jeff Leek and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Regression is probably the most fundamental topic for the data scientist. Before you do any fancy machine learning or anything like that, your go-to procedure is going to be linear regression, or its generalization, linear models. Regression has a rich history, and it goes back to this fellow here, Francis Galton, who invented the term and the concept regression and the term and the concept correlation, which is intimately tied to linear regression. And he did many things, one of which was predicting a child's heights from a parent's heights, a data set that we will investigate a lot just because of its historical significance. And my friend and co-instructor Jeff Leek noted that this example is actually surprisingly still relevant. And here's an article from the American Journal of Human Genetics where they compare modern genetic data using high throughput bioinformatics to the old Victorian era measurements created by Francis Galton, and see that it doesn't do too much better. So anyway, I give you the links there. You can read them over. It's a very interesting and kind of quirky take on modern genetics and genetic analysis, but it also goes back and reminds us about the importance of what Francis Galton did and how ahead of his time he really was. Let's go through a more modern example that's a little bit more similar to what a data scientist would be doing in their day-to-day lives. So if you don't read the blog Simply Statistics, you really should. It's written by Jeff Leek, Roger Peng, both of who are co-instructors in the data science specialization, and Rafael Irizarry, who has a couple classes on edX that you should check out, who's at Harvard, biostatistics. And Rafa wrote this post, was talking about ball hogging and players. And he basically, here has a plot of the percentage of the shots that were taken by Kobe Bryant and the point differential, the game-specific point differential. And he fit a linear regression to it, and he made some of the claims in the blog post, and you can find it and read the full post. But for example, one of the claims was, data supports the claim that if Kobe stops ball hogging, the Lakers will win more. But probably more relevant to this class is he makes this specific statement. Linear regression suggests an increase of 1% in percent of shots taken by Kobe results in a drop of 1.6 points, and he gives a standard error in score differential. So creating this sentence is what a large part of this class will be about. How do you create this sentence? How do you interpret it? How do you, Rafa's adhering to good statistical practice and giving a standard error. And these are the sorts of things we're going to talk about in this class. But I'd also like, just for this example, to think about, not only how it was done, but do you agree with the analysis? What are things that maybe Rafa should have thought about, or what is this a complete analysis? And maybe read the blog post and some of the comments where some of the topics that are germane to regression analysis are covered there. Let's go back to our example where Francis Galton was using the parent's height to predict the children's height and talk about the kinds of questions we can answer. So we might want to use a parent's height and try and predict their children's heights. We might want to find a parsimonious and easily described mean relationship between the parents and child's height. So we don't want anything complicated. We want the simplest possible relationship, and that is what regression is best at. While machine learning and other techniques generate highly elaborate, in many cases accurate prediction models, they tend to not be parsimonious. They tend not to explain the data, and they tend not to generate new parsimonious knowledge, whereas this is what regression is good at. This is what regression is, in fact, best at. We can talk about variation that's unexplained by the regression model, the so-called residual variation. We can quantify the impact that things like genotype information has beyond parental height in explaining child height, and that's related to this European Journal of Human Genetics paper that looked at what residual variation was left after using parental height, or what residual variation was left after using genetics. And then very importantly, we're going to connect this back to the subject of inference. How do we take our data, which is just a sample, it only talks about that data set, and try to figure out what assumptions are needed to extrapolate it to a larger population. This is a deep subject called statistical inference. We have a whole nother class on it in the Coursera Data Science specialization. But we're going to apply the tools of inference, which I'm hoping most of you will have had as a prerequisite. We're going to apply the tools of inference to this new subject of regression. And then here's a fun question that Galton answered, and it's called regression to the mean or regression to mediocrity. And the basic question is, why do children of very tall parents tend to be tall but a little bit shorter than their parents? And why do the children of very short parents tend to be short but a little bit taller than their parents? And this is the famous idea of so-called regression to the mean. Let's look at Francis Galton's data. And I just want to note he first used this data in 1885, and that you should read up on Francis Galton. He's really an interesting character in history in general, and definitely in the history of statistics. Had many quirky aspects to his personality, and he invented a lot of really great things and some things that are not so great. You need to run install packages using R. Here, using R is the package for the book, Using R for Introductory Statistics. It's a great book, and they very kindly packaged all these data sets together in a single R package. So you need to use Using R and then library Using R to get a lot of the data sets that we're going to be talking about. So let's first look at the marginal distribution of the parents. In other words, distribution of the parents disregarding children, and the marginal distribution of the children disregarding parents. Parent distribution is all heterosexual couples, correcting for sex, I guess, by multiplying the female heights by 1.08. Here I give my ggplot commands for creating the two histograms. On the left I have the children's height. The x-axis is in inches. The scale goes from 60 inches to 75. The y-axis is the count, the number of children that fall in each bin of heights. On the right, in the more bluish teal color, I have the parents' heights. I've broken the association by the children and the parents by not doing a scatter plot and only looking at the marginal distribution of the children and the marginal distribution of the parents by themselves. I'd like to use these distributions to introduce least squares, and then we'll build on the bivariate association after that. So consider only the child's height. Forget for the moment about using the parent's height to predict the child's height. We just want to find maybe the best prediction of the child's heights without any other information. Well, probably the best predictor would be the middle, and how could one define the middle? Well, let's give one specific definition. So I'm going to go through a little bit of the notational mathematics, and if that isn't your thing, then wait just a minute and we'll go through a sort of physical experiment to sort of explain it visually. So for the mathematics, let's let yi be the height for child I, where y1 is the height for child 1, y2 is the height for child 2, and so on. My I index here goes from 1 to n being 928 children in this particular data set. So the middle will be the value of mu that minimizes the sum of the squared distances between the observed data, the yi's, and this value mu. That's how we define the middle. It's also related to physics in the so-called physical center of mass of the, for example, of the histogram that we showed on the previous slide. If you thought of those bars as being physical entities having weight and trying to figure out where you would put your finger to balance it out, that would be the physical center of mass. You might have guessed that the answer has to be the mean, right? The center of the data has to be the mean, and that does turn out to be the answer. We'll even go through the proof, though of course if that's not your thing, then you don't have to worry about the proof. Let's use RStudio's manipulate function to experiment with trying to find that center of mass. So I've already loaded manipulate, but maybe I can do it again. I've loaded the data set Galton, and I've defined a histogram function here that executes the ggplot commands to draw my histogram. and it takes as an argument mu, the parameter that we're trying to find. So let me try my manipulate command here. Oh, I don't have ggplot2 loaded. Let's try it again. There it is. Okay. Now because we're using manipulate, I can move my slider around. What I have up here is the value of mu and the mean squared error. That is the sum of the squared distances between the observed data points and that particular value of mu. And because I've added up n things, I might want the average value instead of the sum, so I divide it by n and I get a mean squared error instead of the sum of the squared errors. Okay. So I can move it around, and notice as I get toward the center of the histogram, the mean squared error is going down. And around there might be is the best I can do. 6.34, now it's gone back up. And then notice if I move it way up, it gets large again. There it is at 14. And so what you can do is you can play around and try to find the place that actually minimizes the sum of the squared distances between the observed data points and mu. This would be the point that balanced out this histogram. Now we know what the answer, it has to be exactly at the average of the child's height, but you can actually experiment and see that it minimizes that function. Here I just give the code again, and I want to remind everyone that all the lecture notes are in these R Markdown format where you can get the code. It's embedded in the actual R Markdown file. So there should be a file called index.rmd. You can go into the index.rmd file and get all of the R code for all of the lectures in the entire specialization. Here I'm just reiterating that the least squares estimate is the empirical mean, and I'm showing exactly where that would be and giving you the ggplot commands to create this same plot. Now I'm going to go through the proof that y bar is the minimizer for this equation here as a function of mu. If these kinds of proofs aren't your thing, then just skip it, and in the subsequent lectures the same thing, though I'll give the same caveat before each time I do something like this. If you do intend to pay attention to the proof, you don't need to know either calculus or linear algebra, but ideally you'll be very comfortable with mathematical notation. So for example, if you've had calculus in your past, you've forgotten the specifics of calculus, but you're pretty familiar with mathematical notation and working with mathematical notation, and that's all you need. Okay, so let's go ahead and do it. This is the quantity I'd like to minimize as a function of mu. My yi's are my observed data points. I'm going to subtract and then add y bar. So I've just added 0, changes nothing. So I can have an equal sign there. I can expand this square out, and I get this term, twice the cross product term, and then this term right here. Let's look at this term right here. Notice this doesn't depend on I, so I can pull it outside of the sum, out here. Then notice this guy right here, I can distribute the sum across it, so I get summation yi, and then if I add up y bar, which doesn't depend on I, if I add it up n times, I get ny bar. But notice, I would define y bar as 1 over n times the summation yi. Add up my observations and divide by n is the average. So in other words, ny bar is equal to the summation of yi. So this is 0. That whole term then is 0. Moving on to the next line, I have summation yi minus y bar squared, adding those up, and summation y bar minus mu squared. This quantity is the sum of a bunch of squared things. Has to be positive. So if I throw it out, My equal sign gets turned into a greater than or equal to sign. I've only gotten smaller by throwing out a bunch of positive things that I'm adding. Let's summarize. This function, for any value of mu, is larger than or equal to the specific case when we plug in y bar. Therefore, y bar has to be the unique minimizer of that equation. Up to this point, we haven't used the parent's heights at all. The first thing in this kind of data we would want to do is create a scatter plot of the child's heights by the parent's height. Here I use a ggplot. There's numerous failings in this plot. One of the primary failings is that these points are overplotted. There's lots of different paired parent-child xy values at each one of these specific points. Here I give a better plot where the size of the point represents the number of parent-child combinations at that particular xy location. Here, the color, a very light color, represents a frequency near 40, and a very bluish or darker, relatively speaking, bluish color represents a frequency of number toward that toward 10 or down to 1 at specific locations. So the size of the point and the color of the point are representative of the frequency of parent-child combinations at that specific XY pair, and this is a much better plot because it doesn't lose that information. I would say there is another failing of this plot. For example, I don't put the units of inches on either of the two axes, and I think that's good practice to have the units on the axes, so that's a little bit of a failing for this plot. And if you want to see the code, it's in the R Markdown file. Now, let's suppose we wanted to explain the children's heights using the parents' heights. And let's assume we wanted to do it with a line. Well, in order to make things easy for right now, let's force the line to go through the origin. Specifically, it has to go through the point 0, 0. So in other words, it has a y-intercept of 0. Well, then the line is just x beta, right? Y equal x beta defines a line through the origin. In order to find the best line, all we have to find is the slope. Well, here's how we could potentially do that. We would want to find the slope beta that minimizes the sum of the squared distances between the observed data points, the yi's, and the fitted data points on the line, xi beta. We'll square that distance and add them up, and this is directly analogous to finding the least squares mean that we did just a couple of slides ago. So this is exactly sort of using the origin as a pivot point and picking the line that minimizes the sum of the squared vertical distances between the points on the line. So we're going to use RStudio's function manipulate to experiment with this and see if we can find that line. Now there is a point, and regression through the origin is useful for explaining things because we only have one parameter, the slope, and we don't have two parameters, the slope and the intercept. But it's generally bad practice to force regression lines through the point 0, 0. So an easy way around this is to subtract the mean from the parent's heights and the mean from the child's heights so that the 0, 0 point is right in the middle of the data. And that will make this solution a little bit more palatable, and we'll discuss it later on how this relates to real regression where you fit both a slope and an intercept. Let me just show a picture to illustrate some of these concepts. So here I have a scatter plot where I have some data on the y-axis and some data on the x-axis, and I want to use my x variable to predict my y variable. So this is my x-axis and this is my y-axis. My red crosshairs are my data points. Regression through the origin, in the way that we're doing it, takes the point 0, 0 and treats it as a pivot point. It then tries to find the best line going through the points, where the best line is as follows. me take this line here. It's going to take each observed point y. It's going to calculate the vertical distance. That's yi. That height is yi. Okay? This length is xi, and that point is xi beta on the line. So this distance right here is yi minus xi beta, and then if we square it, we'll get the square distance. So what regression to the origin is trying to find is it's trying to take all of these vertical distances like this between the fitted line and the observed heights, square all those distances, add them all up so that each one contributes equally to the error rate that it's calculating, and tries to find the best slope, because remember, this line is defined by a simple equation, y equal to x beta. When you have a line going through the origin, you only need one parameter, that's the slope. Now, that line's not going to be very good. If you look, the line really should hit somewhere along here. So regression to the origin kind of doesn't make sense. What we're doing by centering the data is we're setting the origin to be right in the middle of the data. So that point now is 0, 0 by subtracting off the means. So it's basically reorienting the axes so that the 0, 0 point lies right in the middle of the data. Now it seems a lot more reasonable to find the regression line that goes through the data where we just consider a slope. So regression to the origin seems to make a little bit more sense if you subtract the means. And we'll find out later that this yields an equivalent to the solution if we were to both fit the intercept and the slope. So let's try and do this with RStudio's manipulate function. And I think because this is one of the central themes of the next several lectures, we're going to go over these points over and over again. They're very fundamental. So I won't show running the code because you can grab it from the R Markdown file, and I'm hoping at this point in the specialization you'll be familiar with running R code. But here's my plot, and over it I have a specific value of the regression line. Notice that my child's height, the indices may get downsampled a little bit in the video compression, but what you can see is the center of the child's heights here is at 0 because I've subtracted the mean. The center of the parent's heights is 0. So I have a pivot point right in the middle at 0, 0. I also want to point out that up here I give the slope beta equal 0.6 and the mean squared error, where the mean squared error is again the sum of the y data points subtracting off the x data point, the parent's height, multiplied times this factor, 0.6. So it's taking each one of these points. Let's take this one, or let's take one that's more centered. This one right here, it's calculating this distance, the vertical distance between the child's heights and the parent's heights multiplied times the slope, calculating that, squaring it, and adding them up. But here again, because there's multiple points at any xy combination, you can think of maybe multiplying this distance by the squared distance by the appropriate number of points at that specific combination because of the overplotting. At the point 0, 0, our line is going to pivot around that point 0, 0 because we're only fitting lines that have to go through the origin because we're only considering a slope. Okay, so let's do it and see how our mean squared error changes as a function of our slope. 0.6 doesn't look so bad. Let's move it to one that's not so good. Okay, the mean squared error has gotten a lot worse, right? So it went from 5.004, say at 0.68. Now let's move it all the way up. Now it's at 5.8. And you can see the mean squared error getting lower right? As you get down to a slope, looks like 0.6 0.6 something is doing pretty well. 0.64 has 5, and then 0.62 has 5.002, so it's gone up. So it looks like about 0.64. What's interesting is the slope of 1 is not good. There's the slope of 1. That's saying you want to predict your child's height, just try the parent's height. Apparently we have to multiply by a factor to get the child's height, to get a better prediction of the child's height than just the parent's height by itself. We have to multiply it by a factor of 0.6 in this case. That's what the slope is doing for us. Here I give the manipulate code, and again, all this code is in the R Markdown file, so don't retype it in from the slides. Actually grab the actual text from the R Markdown file. Now that we've used manipulate to find the slope, I'm going to show how you can do this very quickly in R. The function lm fits the linear model, and if you here I have the code where I use lm. My outcome, my y value, is the centered child's heights, so I've subtracted off the mean, and here is the centered parents' heights, where I've subtracted off the mean for the parents. This -1 says get rid of the intercept because we're talking about regression through the origin, where we forget about a y-intercept, and then telling them that the data set I want to fit is Galton, and it gives me the slope, 0.646. So we're going to talk about this a lot. We'll go through this in great detail throughout the rest of the class. Here in the final slide of this lecture, I just give the fitted line. Now because of how we've forced the model, it has to go through the point 0, 0 for the centered child's heights and the centered parent's heights. So it has to go through the mean of the child's heights and the mean of the parent's heights. I've reshifted the plot so that that 0, 0 is back at the original point. And so here is our line that has slope of 0.646. And now what we're going to do in the subsequent lectures is talk about how we get these, how the motivation behind it, and all the things we can do with this fitted line. We're going to spend maybe the next several lectures talking about this. So welcome to Introduction to Regression. We've actually covered a lot of material in this very first lecture, and I really look forward to working with you for the next couple of weeks.